Hey everybody. So in this video, I want to talk about cylinders and quadratic surfaces. This is often something you would see, for example, maybe in a Calculus 3 course, something that you would see when you're doing multivariable calculus. So first off, I would like to say thanks to all of my friends and supporters on Patreon. I certainly appreciate it. And also I want to give a shout out to wolframalpha.com for giving me permission to use their graphs in this video. Okay, so this is going to be part one of two. So the first thing that I want to talk about are cylinders. So when I think of a cylinder, I often just think of something, sort of a regular shaped, for example, something like a soup can. So, right, this would be some examples of some cylinders. Okay, now in calculus, we think of something a little more generic, a little more general. So our definition here real quick. So a cylinder is a surface that consists of all lines, which are called rulings, that are parallel to a given line and pass through a given plane surface. So I want to look at an example. We'll graph one of these, and then we'll kind of make some observations based on that graph. Okay, so let's graph the curve, the surface, y equals x squared. But again, this is going to be in 3 dimensions. So one thing I want to point out too is notice that only the variables x and y are showing up. Notice there's no z occurring in this equation, y equals x squared. Okay, so forget about this little part here for a second. I'm going to use that just to speed up my graph here in just a minute. Okay, so I've got my x, y, z axes here graphed, and that's where I'm going to try to graph this y equals x squared. And the way I'm going to think about it, and I'm going to use the same idea when we start graphing more complicated surfaces, such as these quadratic surfaces that we're talking about here. So we can use that same idea on those. Okay, so the way I think about it is, so y equals x squared. Well, okay, we are going to graph this in 3D. But first off, I'm going to think about it in 2D. So we know what the graph of y equals x squared looks like in 2 dimensions, right? There's our good old x and y axis. We know that y equals x squared is just going to be a parabola. So that parabola is going to be sitting in the xy plane. Okay, so let's go back up and think about it for a second, though. So the xy plane is kind of like, if you imagine this as being, this x, y, and z, if you imagine this being the corner of a room, for example, that y equals x squared, you can imagine that's sort of sitting along the floor. That'll be where I'm going to graph my first little piece of this. So I'm going to take this little part, and I'm going to put that right there, and imagine that that's the graph. That's that parabola, but it's sitting, again, along the floor of your room. Now, what we're going to do is, to get the rest of the graph, notice that again that the variable z, that the variable z is missing from our formula. So what you can imagine doing is, we're going to take this little parabola that's in the xy plane, and we're going to stretch it. We're going to just make that same image sort of, we're going to stretch it along the z-axis, both in the positive and the negative z direction. So positive z and negative z. And the idea is, if I were to take a horizontal slice, I'm going to keep getting the same shape repeated. So the idea is I can just move this shape along the z-axis. And what I could do then is I could play connect the dots. So again, this is going to extend infinitely, up and down, and also it's going to open. It's going to, just like a normal parabola, right? It keeps extending in the positive y direction. The same thing, our cylinder here is going to go infinitely in the positive y direction. And we could connect these in the back. And this is where we're just getting, again, if we take all these slices, these horizontal slices, we're just going to get this the cylinder y equals x squared. So you can imagine it's kind of like a piece of paper that's not, that you're kind of bending a little bit, and that vertex of that parabola, or sort of, one, the how do you want to say it, the part where the paper's being sort of folded or bent, that's lying along this z-axis. And that would now be our graph of y equals x squared in 3 dimensions. Okay, so notice, again, that variable z is missing, and you can just take that shape, and again, once you have it, for example, in the xy plane, just imagine copies of that moving up along the z-axis and also down along the negative z-axis as well. And this is where I find, these graphs can be a little hard to do in general. So let's talk next let's do one more example. Let's graph y squared plus z squared equals 1. And I'm going to use this exact same idea, y squared plus z squared equals 1. So again, we want it in 3 dimensions. I'm going to start, though, by graphing it in 2 dimensions. So if you think about y squared plus z squared equals 1, well, that's just going to be a circle of radius 1 in the yz plane. So imagine taking the circle in the yz plane, and that's what I'm trying to do on my graph on the left. So imagine that circle is in the yz plane. And again, what we're going to do, notice by using the same reasoning as before, notice that x is not present in this equation, right? The x is missing. So you can now imagine taking that object and sort of stretching it along both the positive and the negative x-axis. So I can just start copying that little circle, and I can start placing it, again, along that x-axis. And again, not the best graph in the world. This is why I would certainly advocate in general for not doing these by hand. But, okay, again, just trying to get the rough idea. And now we could play connect the dots a little bit here. Connect the dots, and the idea is if we were to take for any fixed value of x, so if I take a slice, for example, if this is in the plane x equals some value k, the idea is if I were to take a slice that's parallel to the zy plane, if I were to take that slice, again, I'm always going to get these circles. So it's kind of like that soup can we had at the very beginning, but now it is, it's kind of laying along its side, and its center, that soup can would be centered along that x-axis. Okay, so this is the idea of a cylinder. Okay, so next let's talk about quadratic surfaces, and here we're not going to do a ton of things. We'll try to maybe graph one quadratic surface, and then we'll go from there. So again, quadratic, just like in 2D, has to do with degree 2. So the definition here, so a quadratic surface is the graph of a second degree equation in 3 variables, x, y, and z. And the most general such equation is, again, we're just sort of looking at all combinations where we get degree 2, degree 1, or constants. So we would have ax squared, again, a, b, c, d, e, f, g, h, i, j are constants. So we've got ax squared plus by squared plus cz squared. And then we've got all combinations of 2 variables. So dxy, eyz, fxz. So again, notice if you think about the powers on those, 1 and 1, those add up to degree 2. And then we've got the other possibilities, just something multiplied by x, something multiplied by y, something multiplied by z. So again, gh and I respectively. And then we could just have a constant, and we could set that equal to 0. Okay, now if we use some translations and some rotations, what we can do is we can actually take this sort of long general form, and we can put it into what are known as our 2 standard forms. We would have ax squared plus by squared plus z squared plus j equals 0. Or we could put it into the form ax squared plus by squared plus iz equals 0. And notice what's happening here is, you notice our first standard form, both the x, or all, I should say all of the x, y, and z are being squared. And notice in our second one, we have our x and our y being squared and our z only being raised to the first power. Now, one little remark too with this last form here, it doesn't have to be that z is the only thing that's the variable being raised to the first power. What we want is we want two of our variables being raised to the second power and one of our variables being raised to the first power. So for example, I could have had, instead I could have had an expression of the form, ax, so that's going to be my variable to the first power, by squared plus iz squared equals 0. That would still correspond to this second form. So again, you've got two variables squared. One of your variables is to the first power. Okay, so maybe just worth pointing that out. And again, that's just going to just sort of rotate your object in that XYZ plane. Okay, so some books use what are known as traces to help produce these three-dimensional graphs. And the idea is what you're doing is you're taking a bunch of 2D graphs and you're trying to combine all of those 2D graphs into a three-dimensional object. That's the idea. I would argue this is largely unnecessary now simply because of the advent of graphing software that is by and large pretty available and accessible at this anymore. So I would say in general, if you have access to graphing software, by all means use it. It'll save you a bunch of time. But just for completeness' sake, let's look at how you would use traces to produce a graph. So I'm going to try to graph this quadratic surface, z equals 4x squared plus y squared. Notice again that would correspond to this second form that we mentioned here. After we obviously put the terms involving x and y to the right side and we isolate our z. Okay, so there's my x, y, and z. Okay, so the idea for traces, what you're going to do is you're going to take each variable and you're going to set it equal to some value k. So we could set z equal to k, and then we would graph k equals 4x squared plus y squared. Likewise, you could set x equal to k, and then we're just graphing something in the zy plane. And lastly, you could set, for example, y equal to k, and then you're graphing something in the xz plane. Okay, so let's see if we can't think about that a little bit more. Okay, so again, same idea. Just like I said, we're going to let x equal some value k, and then we're going to think about that resulting graph, and we're going to graph that's going to be it's going to be parallel to the yz plane, and it just depends on what value of k you get. Okay, it's going to depend on what value of x equals k you use, and that's again going to give you something parallel to the yz plane. And you could do the same argument if you let y equal k. You think about that resulting graph and graph that parallel to the xz plane. And likewise, we could let z equal k and think about that resulting graph and graph that parallel to the xy plane. Okay, little disclaimer here. My graph is probably going to be a bit of a hot mess, which is why I steer clear of this process in general. I would just, again, go to Wolfram, for example. Desmos is also really great graphing software, but as of now, as of me making this video, they do not do three-dimensional graphs. I assume that'll probably change in the future. Okay, so let's go back to z equals 4x squared plus y squared. So all I'm doing is, I'm going to do sort of a couple different cases. So I'm going to think about letting each variable equal 0 and then something more generic like k. So notice if x equals 0, well, if I replace here with x equals 0, I'm simply going to be left with z equals y squared. And again, that's just going to be a parabola in the yz plane. Okay, so that's going to be a parabola in the yz plane. So if I go back to graph that, maybe I'll graph these first couple parts in red, and I'll graph these next couple parts. Maybe I can graph those in, for y, I'll try to graph that in blue, and maybe the last ones, I'll try to put those in black, just to sort of separate them. Okay, so if x equals 0, again, we just get z equals y squared, and that's going to be in the yz plane. So we're going to graph those in red, we said. So the yz plane, you can think again about the yz plane as sort of like that back wall. It's going to be there. So, okay, so let's graph that one. So again, this is where it's going to start getting a little rough. So I've got a parabola, and again, just think about that as being in that yz plane. And this would correspond to where x equals, again, 0, okay? So that parabola is going to be going right through our origin, or through the point 0, 0, 0. Well, what happens if we use something more generic? For example, just x equals k. Well, here I reordered it. Well, we would have 4k squared plus y squared. Or equivalently, I would have z equals y squared plus 4 times k squared. So all this is, again, this is going to be a parabola, right? We've got z equals y squared plus this 4k squared. So all that's going to do is it's just going to shift it up a little bit, okay? So we've got z equals y squared plus some positive value, which is going to give us a parabola shifted upwards a little bit. Okay, so this is where it's going to get kind of rough. I'm going to delete this here in just a second. Let's suppose, for example, this was the value x equals 1. So in that case, if we used x equals 1, all right, if we go back down here, we would have z equals y squared plus 4. So what that would do is that's just going to shift my parabola up, and again, it's still going to be parallel to this yz plane, but it's going to be shifted up 4 units. And again, I'm just getting, I'll make that one dashed. I'm just going to get another parabola that's been shifted up, but sort of pulled out towards us a little bit, if you imagine, again, corresponding to the plane x equals 1, still parallel to that yz plane. And again, this is where they start getting a little confusing to me to graph by hand. It just gets very cluttered. So let's try to get rid of some of this. Okay, but that's the idea. Let's keep going here. Let's try to do a couple more. Okay, so let me change my color here. Do I have blue? I had blue somewhere. There we go. Okay, so if y equals 0, again, we're going to get this parabola. So I'm just replacing y with 0. Now we're just left with z equals 4x squared. So again, this is just going to be a parabola, but now it's going to be in the xz plane. So let's go back up. The xz plane, you can think about that as kind of being like this left wall. So that's going to be, we'll get another parabola here. It would be a little more narrow because it's got that coefficient of 4. So there's that. And then again, this is in the, now you could think about this again as being in that xy plane. And the same thing, the same idea. If I let y equal k, again, I'm just going to get these parabolas that are shifted upwards. Okay, let's look at one more. Let's let z equal, well, two more, I should say. Let's let z equal 0. And if I let z equal 0, well, I'm just going to substitute in 0 on the left. And that would give me that 0 equals 4x squared plus y squared. Well, the only solution to that is when both x and y also equals 0. So it says, well, z was equal to 0. We know x has to be 0, y has to be 0. So it says again at that point 0, 0, 0 is on the graph. So we know that it's sort of bottoming out right there at the corner of the room or at the origin 0, 0, 0. Now this one's going to be a little bit different because if I let z equal k, in this case, well, if I take my original equation, right, I'm just going to replace z with k. We'll get k equals 4x squared plus y squared. And those are simply going to be the graphs of ellipses, right? So normally we make that constant equal to a 1. So we would do some arithmetic that would tell us how far out, kind of how narrow our oval is. But it says if we take a horizontal slice z equals k, we're now going to be getting ellipses. Okay, so let me try to do that. So it says if I take a horizontal slice, so it's going to be horizontal to the xy plane, I'm now going to be getting these ellipses. And well, as z increases, those ellipses are going to get larger and larger and larger. So we'll get these little ovals, and you're kind of getting, I don't know, how would you describe this shape? It kind of looks like the bottom half of a bullet or something, right? Bullets are kind of rounded off at the end. It looks like you're kind of getting the bottom half of a bullet. But again, as it opens, as you increase along the positive z-axis, again, these horizontal slices that are parallel to the xy plane, those ovals are just going to get larger and larger and larger. Okay, so that would be a rough graph of z equals 4x squared plus y squared. And I did use Wolfram here to produce this graph. And you can see where you're kind of getting the shape. One little remark, I don't quite know why it did it. I use Wolfram a little bit, but I'm not intimately familiar with it. So we do have our z-axis. Notice that our x-axis is now here and our y-axis is here. So those did get transposed a little bit. So just do be aware of that. I don't think it happened in some of my other graphs coming up. But again, you can kind of see this if you focus in on this bottom portion of the graph. If you focus in on this bottom portion of the graph, down here, that's where we're getting this portion of the graph. And then it just cuts it off just because of the restrictions based on the, on the values for y and the values for x. Okay, so that would be a graph of z equals 4x squared plus y squared using some graphing software. So it's going to turn out that there are 6 basic quadratic surfaces, and I'm going to talk through these really quickly and just give some examples. Okay, so the first is going to be the ellipsoid. That's going to be of the form x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Again, a, b, and c are constants. So I did one example. Here my a value is equal to 2, so 2 squared is going to be 4. And then I simply let b and c equal 1. And you can see you get this ellipsoid. It's kind of like an egg-shaped object. If a and b and c were all equal to 1, we would just get a nice perfect sphere. Okay, but if either a, b, or c are not equal to 1, if any one of those are not equal to 1, you're going to get this more elongated shape, which is the ellipsoid. Okay, we can also get a cone, and that corresponds to z squared over c squared equals x squared over a squared plus y squared over b squared. And again, you could have x on the left and then z and y on the right, or y on the left and x and z over here on the right as well. And that's just going to, again, just sort of change sort of the direction that your cone, where it's opening up and down. So I used z squared equals x squared over 4 plus y squared, again, just an example. And you can see this infinite cone that we're getting. There's 2 pieces of it. Okay, so there's the elliptic paraboloid, and that's actually just like the one we graphed using our traces. So here that's going to have the form z over c equals x squared over a squared plus y squared over b squared. So here we have z equals x squared plus y squared, which is almost what we had up here, right? We had 4x squared instead of just x squared. But you can see how it's got that almost that same shape. It's just, just because we had that coefficient of 4 on the x squared, it's got a little bit of a slightly different shape. But here I just had the coefficients on both z, x squared, and y squared equal to 1. And again, you can see that same rough shape that we were producing a second ago. Okay, so in this case, again, notice that our x and y are still interposed here. Next up, we have the hyperboloid of one sheet. And this is going to have the form x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. So notice two of our variables are positive, and one of them has a negative sign in front of it. So again, I just let a, b, and c all equal 1 here, just to give kind of a basic example. And here you can see it almost looks like one of those cones, but it doesn't just quite come down to a point, right? There's a little bit of a little bit more space in there, but moderately similar. Okay, so, and I believe last but not least, we have the hyperbolic paraboloid z over c equals x squared over a squared minus y squared over b squared. These kind of remind me, they kind of look like a saddle, you know, something you throw on your horse and ride around Texas on. So I just simply let, again, all of my variables, or my constants rather, c, a, and b all equal 1. And here I've got graphed z equals x squared minus y squared, and you can see that corresponding shape. Okay, so, oh, no, we did have one more. My apologies. The hyperboloid of two sheets. So here we have negative x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. And notice, in this case, we have two of our variables with negatives and one of them with a positive. And that's where we're going to get this hyperboloid of two sheets. And notice in this case, it kind of looks like a little bit of like one of those infinite cones, but we've got some gap. They don't quite all touch up. Okay, so those will be our 6 quadratic surfaces. And if you remember the conic sections from geometry or from pre-calculus or calculus, those we talk about we kind of get these graphs in 2 dimensions. We get the parabola, the ellipse, the circle, etc. You can think about these quadratic surfaces as being sort of 3-dimensional analogs to those. Okay, so I'm going to pause this video in just a second, but before I do that, if you want to try some questions on your own, I've got a few questions here, and in part 2, I will produce solutions to all of these. So the first couple questions, these are going to correspond to those cylinders. We can sketch z equals 4 minus x squared minus y squared equals 0, and then z equals cosine of x. So that one feels a little different, but you just do the exact same thing. We're going to talk about doing those traces. So we'll use those traces to sketch the surface x squared plus 4y squared plus z squared equals 4. And then you can identify that surface by trying to match up which one of those 6 quadratic surfaces it goes with. I would even maybe start there, because then you can narrow it down, and at least in that case you'll have a clue as to what it should look like. And lastly, we've got these 2 questions, 5 and 6. We're going to put the equations into standard form and classify the given surface. So we're going to put it in one of those 6 forms we saw just a second ago. We'll classify it, and I will go ahead and put them in Wolfram to sketch them. Never hurts to go ahead and sketch them and see what they look like. A little hint on this last one, because it's not, notice in the other ones we saw, we just had those either one of our variables to a first power and the other 2 squared, or like in number 5, all of our variables are being squared. Notice we have a bunch of these extra terms. So in this case, what you're going to have to do, I'll give you a little hint on the first step. Think about completing the square, and that should get you going in the right direction.